This episode is sponsored by Brilliant. It's always amazing to watch a rocket take off from the ground and fly up through the clouds into space. But why not start off higher up to begin with and launch from above the clouds? So today we are back to the Upward Bound series to cover a topic that's been requested a lot, which is why we don't launch rockets from blimps or planes, and if we could. Since we've been discussing floating whole cities or even continents in the sky of late, it felt appropriate to cover floating launches. Plus, we've been spending a lot of time in the far future in recent episodes, and some folks have asked for an episode about near-future prospects and grounded in the emerging technologies of today, and this topic seemed appropriate, except for the grounded part obviously. 1 out of 2 isn't bad. We'll also be taking a look at JP Aerospace's Dark Sky Stratostation, an enormous lighter-than-air lifter that offers a somewhat slow but very cheap route to space, some non-space applications of these technologies, and we'll jump out a little further ahead in the future to look at what might be on the table for aerial launch systems if we've got an abundant source of power. We should start though by asking why you'd ever want to launch from higher up, because you definitely do if you can, but not for the reasons most folks think. As we've mentioned throughout the series, the big challenge for launching from Earth isn't getting up high. It's getting up to orbital speeds and doing it through a thick atmosphere. Atmospheres are handy for planes and air-breathing craft in general, but it's very hard to get up to orbital speeds with that approach. And like a lot of hybrid launch concepts, each stage operates differently, involves different and heavy equipment cutting into your payload, and more possibilities for critical failure. That's a pretty big reason why we prefer single-stage launch craft where possible, and why we launch from the ground rather than from higher up. It's where all our assets are, and even building up high on a mountain near the equator, the best ground-based launch location, tends not to be worth the problems that come with trying to make, staff, and maintain that facility compared to something within commuting distance of our population and industrial centers. That makes something like a blimp carrying a rocket a very attractive alternative, because you launch the rocket and blimp from a facility and then launch the rocket once the blimp achieves the necessary altitude, but it requires a lot of blimp to lift that much rocket. Now I want to emphasize, you're not lifting that rocket up because it gets you several kilometers toward your goal of orbiting a few hundred kilometers up. Rocket launches aren't about height. They're about energy and speed, and that blimp isn't adding much to one. It's cutting down on the amount of air you have to smash through on your way out and up to speed. That speed matters. Stuff stays in space because it's spinning around the planet fast, not because it's high up. If you lose enough velocity, you'll just fall out of orbit. Now the alternative to a blimp would be a rigid aircraft moving at high speed that a rocket launched from, and that offers a nice speed boost while cutting down on the air you have to plow through, and we'll look at that today too, and more when we get to spaceplanes next month. But the short form is that any launch system is dependent on how much thrust and specific impulse it can offer, and a good rocket fuel offers around 400 seconds of specific impulse. As a reminder, specific impulse is measured as the time that rocket could sustain a thrust equal to gravity, to basically hover in place. Needless to say, we burn the fuel a lot faster than what's required to levitate them. An air-breathing plane can do way better in terms of thrust off any given fuel because first off, it doesn't have to include any oxygen to burn that fuel with, while a spaceship obviously does. And if you're burning something like hydrogen, oxidizing it and producing water, well, there might be H2O, but those 2 hydrogen atoms weigh a lot less than that 1 oxygen atom does. Moreover, flying through the air, you don't need a propellant, since you can use a ramjet. You suck air in and shove it out the back to add momentum to your craft, while you can't do that in space. If you want to move, you have to throw mass out the back side, and you have to be carrying it with you. This is the fundamental limitation of the rocket equation. So ideally, we'd want to get up to speed in the atmosphere, where we can take advantage of all that air rather than carry all that oxidizer and propellant. However, there are some big constraints on trying to use that air, not to mention glide through it at supersonic speeds, though we'll save discussion of things like ramjets and scramjets for the spaceplanes episode. Key thing, to orbit Earth, you need to be moving 7.8 kilometers per second, or about Mach 23, and you need to get up to and maintain that speed while plowing through air, so anything you can do to cut into that helps a lot. But starting off at Mach 1 and getting to Mach 23 is not the same as having done 1/23 of your work already, as kinetic energy increases with the square of velocity, so you're only about a 500th of the way there, and that's ignoring drag and the whole rocket equation issue too. So it's saving energy, but not a huge amount, and the same applies to being near the equator, where you can add the Earth's spin, about Mach 1.3, to your ship. Combining the two, plus getting several kilometers of thick air out of the way, makes it very tempting to launch something carrying a rocket that will fly down to the equator and get as fast and high as it can go, then let the rocket off. But it's not such a huge benefit that it's generally seen as making up for all the extra problems and costs and points of possible failure that adding those in will add to your launch. That's obviously debatable and hinges on technological and economic factors that are always in motion too. For instance, our best lifting gas for a blimp is hydrogen, which is also our best rocket propellant, but we tend not to use it for either as much as we could because it's a bit of a nightmare to work with, and we don't see too many blimps because helium is quite rare on Earth, despite that it's the second most abundant thing in the universe, and tiny helium atoms tend to leak through materials, so blimps can get rather expensive. This is one of the reasons we like satellites. For communications you want a very broad range, which is mostly about being up high, and towers are expensive. We can float communication balloons up higher, but it's a big thing that can be blown around by the wind and is leaking expensive helium. If we get better at managing those issues, it would make a lot of sense to stick a big floating solar-powered communication balloon over a city to provide cell phone and Wi-Fi coverage, instead of an expensive geosynchronous satellite tens of thousands of kilometers up. The few hundred kilometers to low orbit, or the tens of kilometers that get you well above weather issues for blowing your balloon around or shading its solar panels from sunlight, offers a great deal of cost savings and decreased signal time. Indeed, various projects looking at those options are also reviving thoughts of maybe doing these blimp-style rocket launches, as they rely on a lot of the same tech and infrastructure. But before we jump into future projects, let's discuss some existing ones. One of these is the Rockoon, a combination rocket and balloon. And those of you who catch our monthly live streams might remember back around the beginning of the year, someone asked a question about those that got garbled as vacuum raccoons, which was confusing but still sounded like an awesome idea, as raccoons are pretty cool. But the Rockoon is an old idea predating the space program, something James Van Allen came up with, for whom the Van Allen belt around Earth is named. It's a simple idea, and it had to be since it predated computers. You stick a rocket on a balloon, and instead of lighting the rocket immediately, you let it float up and then ignite. The main problem then was that we couldn't really steer them, and rockets were far more prone to blowing up back then, so it required a very large, safe area around your launch site, since people tend to object to having a ton of flaming debris land in their front lawn. Needless to say, in the 70 years since the notion was suggested, we've made a few technological improvements, and quite a few companies have been taking a second look at this concept in the last couple of decades, and more in the last few years as CubeSats and other small satellites are making small private launches a more tangible business model, especially after the success of private launch companies like SpaceX. This channel tends to focus a lot on very large and high-capacity launch approaches, but in terms of developing a real and sustainable space economy, small launches that many different companies with many different approaches can get into might be the better way to blaze the trail. Which is kind of amusing since these smaller rockets and balloons would generally not leave the giant flaming blazing trail in the sky that a normal rocket would. They are handy too though, because as I mentioned, we don't build launch sites in optimal places like mountaintops because they are far from our population and industrial centers. But these giant booster rockets we use can't be too close to cities either, whereas these small ones can be launched much closer, and for a rockoon, could be released right in the middle of a city, since they could drift before the rocket turned on. Nor do they have to drift. Again, this isn't 70 years ago. Blimps always had propellers, and we can easily put remote-controlled balloons up, same as we can drones. And we do have the option for heavier-than-air powered flight too, not to mention all those other methods of getting things to stay in the air we discussed in Cloud Cities a few months back. Fundamentally, it will save you mass to follow such paths. It's just whether or not it will save you money and cargo. As with all hybrid launch systems, you have to worry about the cost of the hybrid, the weight, the extra chance for failure, and choke points on transport too. For instance, let's just say we had a big sky platform big enough for airplanes to land on and rockets to take off from. You're saving fuel this way, assuming the platform isn't burning any, but you need people up there. You need both the plane and the rocket. You need to unload people and cargo from one to the other on the platform, and that all takes time and money too, to build and maintain and operate, and to ensure against the extra risks of something going wrong. And every person you add on site to minimize problems switching stages is introducing more mass, all their supplies and living room, and even the weight of the air in their pressurized quarters. But those problems can likely be tackled. For instance, remote-controlled robots minimize how much crew you need up there. We'll talk about some high-tech paths in a moment, but we've got a serious option on the table for modern tech from JP Aerospace that is a type of stratostation, designed to operate 140,000 feet or 42 kilometers up in the air, called the Dark Sky Station. This thing is pretty large, bordering on a megastructure, though modest compared to other launch megastructures we've discussed, like the Lofstrom Loop or Orbital Ring. It is part of their airship-to-orbit system, and is about 3 kilometers across, looking like a big starfish, which is appropriate given its suggested role in getting us to the stars. Airship-to-orbit relies on a 3-stage approach. The first is an airship that uses a hybrid of buoyancy, aerodynamics, and near-vacuum propellers to get off the ground and reach the Dark Sky Station. Up there, folks and cargo depart, Stage 2, and we have another kilometer-scale spaceship waiting that can only exist and operate way up there where there's virtually no air. Instead of rockets, you get on these huge secondary airships for Stage 3 that will ascend to orbital speeds and heights by a mix of chemical and electric propulsion, but takes several hours to do it, rather than the minutes a rocket would. This is a downside, but not a very big one, particularly considering how cheap the launch cost is. They estimate about 31 cents per kilogram launched, rather than the several $1,000s a kilogram we pay now, and it is a bulk lifter designed for carrying many tons. I don't know about you, but I don't mind taking a day to get to orbit if it costs me as much as a bus ticket. Needless to say, it's not ready for launch yet, but it has no really huge technical issues requiring massive advances, and they promote it as a pay-as-you-go approach, since many of the steps involved to full-scale deployment have economically viable options too. Of course, we have some other big options like the Lostrum Loop or Stall Tram and mass drivers we've discussed before, and those all feature long lines that you accelerate down that either end in the upper atmosphere or even start there. Some of those concepts already contemplate using a launch track that's floating by buoyancy anyway, so a multi-kilometer long track floating up there is an option too. What's more, since those are essentially electric, we could be supplying the power from groundside of some long power lines that act as tethers for helping keep the thing in place and to lift people and cargo to it. If such tethers are impractical, you could still fly up there and either get your power from solar energy or beam it to them. These things are quite big after all, with plenty of room for panels, or you can install a rectenna for power beaming, either from groundside power stations or power satellites, like we discussed in the episode of that name. Microwave beaming mostly requires a big thin mesh to act as the rectenna, and that's pretty easy to incorporate into a giant blimp. But if you're supplying power from elsewhere, why only use it for launch? As we've mentioned before, we can make either atomic-powered planes that never have to land, or ones where the energy gets beamed in. There's nothing high-tech about a nuclear plane, we just don't build them because they make folks nervous. And legitimately so too. They're pretty safe, especially the newer designs, but concerns about them aren't the same as the usual over-the-top technophobia we often see with atomic energy. They obviously still can crash, and having a kilometer-long floating spaceport land on you is bad enough without adding uranium to the mix. However, just because something is flying around under power doesn't mean it has to go anywhere. Ignoring the helicopter or helicarrier option, you can just have one circle around over a spot off the coast of whatever city it services. Because it's moving at a set speed normally, albeit in a loop, your ground-based connection flights can find optimum times to land on it without needing to match its actual speed, meaning it can get away with going much faster than the things needing to rendezvous with it. But also, because it's moving very fast, especially if it's flying counterclockwise, in the northern hemisphere anyway, on that southern edge of its circular path, it gets to add all that speed to the Earth's rotation and launch things to space with that. If it's enough speed, and you've got strong tensile materials, it might even be fast enough to match up directly to a skyhook or rotavator, but at the least it would give a big head start to any scramjet that was seeking to do so. We'll get to that option more in the Spaceplanes episode though. I mention it because if it is circling, you could potentially have a cable running up to it like a whirling slingshot, and if your materials can handle that and the air drag issues, you could have an ascender run up that line from your groundside spaceport that basically just had a sail. Indeed, you could have multiple layers of these, each higher up and probably wider out, though it need not be concentric. You presumably want your turn radius low enough that you can just tilt the floors on the sky platform a little, so everyone just feels a little heavier walking around it. You accelerate when turning, and if you're trying to keep that platform cruising around at a few kilometers a second, about half orbital speed, that turn radius needs to be almost 1,000 kilometers, though considering how fast you're going, you complete a circle about every half hour. So you could potentially have a big one that serviced the northern Atlantic, whirled around at about half orbital speed way up in the stratosphere, and local regions would have more modest loops for letting subsonic or modestly supersonic planes land on, which would also be a very handy way of moving around Earth too. Something like that is fairly ambitious, but a good reminder that when you can make and move a lot of power cheaply, many constraints are altered, and new options that would seem absurd in the past suddenly become viable. As we'll see when we get to moving stars around next week, there is a big difference between that which seems absurd because it breaks known physics, and that which simply seems so because it's like explaining a skyscraper or railroad track to someone at the dawn of the Iron Age, when building large structures or roads out of iron and steel would simply seem absurd, because of the relative scarcity and cost of that material. So is there a future for these kind of approaches? That's hard to say. They are not pie in the sky as we just saw, but the question on any new technology isn't just if we can do it that way, but if we've got something better, and that can be very hard to predict since it relies on a fairly solid image of the specific tech and economics of not just one, but two or more technologies. We've seen some of the other ones like mass drivers and orbital rings in earlier episodes, and of course we've seen what reusable rockets are shaping up to do already. The ideal one, or what most of us tend to view that way from science fiction and modern air travel, is a craft you can get on at your local airport, and which flies directly to a space station, and as mentioned, we'll be looking at space planes next month. One advantage these approaches have is they do have direct, smaller applications in our economy, which gives a good pathway for development to something grander. As I've mentioned before, a lot of things we can do with satellites we can do with big floating balloons too, like solar shades or mirrors for warming or cooling the planet or regions of it, or power generation by wind or solar. They are fundamentally better than geosynchronous satellites as communication hubs too, because while light moves fast, even light takes a noticeable time to get up to geosync and back, and that's a lot of distance, not to mention air, to move a signal through. So I do think there's a good chance we might see some serious advancement and utilization of some of these pathways in the future, and maybe even some of the more ambitious approaches we looked at in Cloud Cities or for colonizing Venus and Neptune. Not as fast as a rocket, but maybe safer and cheaper, and if the trip takes longer, you have to admit, the view would be pretty awesome. We were talking today about how it takes far more energy to get up to orbital speeds than supersonic speeds, even far more than the usual velocity squared formula for kinetic energy implies, and that can be quite daunting in many ways. The orbital energy of, say, a 1-ton car is about 30 billion joules, which sounds like a lot, but is only the chemical energy contained in about 250 gallons of gasoline, or about 2/3 of a ton, less than the car. It can be a bit confusing why most of our launch systems require dozens of times more fuel than payload. To understand why this is so, and why various launch systems are often more practical, it helps to have a good grasp of concepts like energy and momentum conservation that dictate everything from orbital mechanics and rocketry to mundane matters like your car's fuel efficiency. That's where Brilliant's courses on topics like classical mechanics can help you out, with interactive quizzes and visual explanations of topics. All of their courses include handy quizzes to check and improve your knowledge, like their one on rocketry. In addition to many great courses like that, they have fun daily challenges in math, science, and engineering to encourage you to challenge yourself every day. If you get stuck, there's a community of thousands of other users that are discussing the problem and writing solutions. If you'd like to learn more science and math, go to brilliant.org/IsaacArthur and sign up for free. And also, the first 200 people that go to that link will get 20% off the annual premium subscription, so you can view all the daily problems in the archives and unlock dozens of interactive problem-solving courses. Before we get to the upcoming schedule, I was mentioning a moment ago how handy it can be to have a community to discuss ideas and solutions with, and it's a very integral part of this channel. Indeed, it's our communities on Facebook, Reddit, Patreon, and the SFIA website's new forums, where we draw not only most of our new topics, but most of the crew who help me out brainstorming, writing, editing, and animating these episodes these days. If you're looking for a place with folks who share your interests to have a polite chat or ask questions, try out one of those communities linked in every episode's description. So next week we'll be talking about propulsion and launches again, only instead of how we get off Earth to explore the solar system, we'll be talking about how to move entire solar systems to explore or reshape the universe in Fleet of Stars. The week after that, we'll be heading back to the Outward Bound series to look at colonizing black holes, and we'll see if these objects, most notoriously the most dangerous places in the universe, might turn out to be rather inviting places to live. For alerts when those and other episodes come out, make sure to subscribe to the channel. And if you enjoyed this episode, hit the like button and share it with others. Until next time, thanks for watching and have a great week.